So hi everyone. Today I'm going to talk about consistent GW practice, especially the GW code developing our code. So the goal is not like introducing GW theory, but like in practice, hoping to make like people to be able to have a reference to look up and then to learn if they want to use the GW in our group, like what's the thing that they had to do. So first of all, I will define what is the problem we're talking to, and then I overview the real material simulation in this UGF code, which is temporary. Our code is called UGF2, and then I will describe the consistent GW in UGF2, how to set up the parameter file, and like what kind of parameter you should be aware, what stuff you should check, stuff like that, and then I will go through one example so we're interested in electronic structural simulation for real materials, not the model Hamiltonian. So real material you can like naively categorize as like molecular and solid. The molecular is essentially just a finite system. You have an isolated molecule, and that's it. That's the only thing. Like that's the system you're going to solve. And for solid, you assume this isolated atoms or molecule got repeated along 3 direction or 2 direction, either 3D or 2D. So you have this infinite periodic unit cell. Then what defines your system is atoms in a unit cell as well as the translational vector where how your unit cell repeat. And then the approximation we're going to implicitly use is the Born-Oppenheimer approximation, which we assume the nuclei in the solid can be assumed to be stationary, so that we can neglect the kinetic energy of the nuclei, and the Coulomb torsion energy between nuclei is just like a constant to your total energy. So the corresponding electronic Hamiltonian of an n electron system with n nuclei is just looks like this. If there's no relativistic effect, you have this kinetic energy term from the electron, the Coulomb interaction between electron and nuclei, and the Coulomb interaction between electrons, which is this part is typically the one that make the problem intractable. So with the same approximate Hamiltonian, we can write this in a second quantization and in different bases. And certain bases could benefit certain electronic structure method for later like memory wise, or like algorithm itself could have a better complexity, stuff like that. So I'm just list several example like for this position basis. This is your one body Hamiltonian, just this two body U R minus R prime, and then this is your one body Hamiltonian, position basis. And for a localized atomic basis, you expand your Hamiltonian using this localized atomic basis, which is R is the unit cell index, is I is the orbital index. So you sandwich this with your Hamiltonian. This is the Hamiltonian what you will have, and this or the matrix element, how this matrix element are evaluated in practice. So this is like pretty similar to this multi-orbital model in a realistic manner. So you neglect all this non-local if you neglect all this like non-local Coulomb interaction, then this will become a multi-orbital model. And in addition, because we have this translational symmetry invariance, we can also expand our Hamiltonian using this block localized atomic basis. Essentially, we transform this atomic basis to this block orbital basis by this Fourier transform, such that this becomes a block wave, and then this corresponding Hamiltonian now it becomes diagonal in the K space, which is one of the advantage of using this basis. And in UGF2, we're going to use this basis, but keep in mind this is not unique. You could always transform, go to different bases, and for sometimes, like for sometimes you could actually improve your algorithm. And this is just what UGF3 is assumed, and then this is what we're going to work on, and what PySafe is working on actually. So UGF2 is the many body preparation code for periodic systems, also for molecules if you want to do it. So essentially what it does is once the Hamiltonian have been computed in this atomic basis, this UGF2 will perform a many body perturbation theory using different many body perturbation solvers. And the solver could be Hartree Fock, GF2, or GW. So essentially, this many body perturbation self-consistent loop consists of this Dyson equation, which use this green function depends on your self-energy, which contains all the electron correlation effects. And then the self-energy is also a functional of your Green's function. And the form of this functional depends on your many body perturbation solver. So you in this UGF2 code, you could choose different functional, which as like as GF2, H4, or GW, and then you keep iterating both these two equation until the self-consistency is achieved between Green's function and self-energy. So in this code, we assume block Gaussian type orbitals as the one particle basis. Although in general, the code doesn't care that much as long as it's discretized basis. We also assume the matrix element, especially this one, has already been decomposed into a 3-index Coulomb integrals. Especially in PySy, we're using this density fitting, but in general, as long as you decompose your interaction as this form, how you get this V doesn't matter. You could just parse to the UGF2 code and it should just work in principle. And for all the dynamic quantities, this self-energy and Green's function, we use the intermediate numerical representation and sparse sampling technique to represent to expand them. So this is the part I'm going to focus on today. So we're going to run once the input is the matrix element of your Hamiltonian the input matrix element of your Hamiltonian. So once these are computed, and we're going to run this many body perturbation theory using this UGF2 code. And the code is written in C++, and also for some functionality also support CUDA. So once you read this input, and then we'll do this consistent loop, and then the output will be the Green's function and self-energy. But in practice, this is not the only step in the real material simulation. Of course, you first have to define your problem, and the problem consists of the atoms in your unit cell, and then the translational vectors. And then for these two, in numerical simulation, you need to choose the Gaussian basis. As I said, at this step we already assume we have the matrix element computed, but what are the bases of this matrix element will depend on your choice of Gaussian basis. And this is a periodic system in the expanding the block way, so you have to choose your K-mesh. And then once you define your problem, you have to compute the matrix element of your Hamiltonian. And in this step, we're using Python script, storing this UGF2 script, and this init data df.py, and this is based on the PyCF. And this one will calculate all the matrix element of your Hamiltonian, as well as this density two-body integrals. We'll store everything in the HDF files, and then this UGF2 C++ code will just read all of them, and then do the calculations, and returning Green's function self-energy. At the end, this is not just end of story at all, because if you want to have a paper, or if you want to analyze your result, you need to extract the band structure or Fermi surface, or do a sort of post-processing based on your resulting Green's function self-energy. So this part of them are in Python script, and part of them in C++. You can do the interpolation on high symmetry K path, and then do a continuation to get the state of the state or this stuff. But today I'm just going to focus on this, and then it would be other talk by me or by someone to share other steps. So how do you build the UGF2 code? This is in the CQMP GitHub repository. This or the code has a dependency for CMAC, and then of course F score, eigen, HDF5, and CUDA is optional. So you basically load all the necessary libraries. This is just like one of the building example on Poly. So you can just load this build environment intel. So you can make everything. Once you load this, everything almost the HDF5 eigen, like all of this will be loaded automatically. Then you clone this and then go to this folder, build, and then do the CMAC, the sender CMAC. So one thing, there's two things. This one, there's two ask CMAC to use OpenBLAS or whatever BLAS or LabPy library as a backend for some of the algebra library, especially like this dense matrix product. So in most of the case, what I observed is it could give us some speed up, but it is not necessary. It will still, even if without this two line, it will still work. Of course, if you include this two line, you need, of course, need to load OpenBLAS as well. And it's with CUDA equals to we'll enable CUDA partially powered GW solver. If you don't have CUDA, if your machine doesn't have GPU or doesn't have CUDA compiler, then you should just remove this line. So these are the basic parameters. Like there's a lot of them, but you don't have to memorize all of them. And you can always just do dash help to check all the complete parameter list. So essentially, what I want to emphasize is these three files. These three HDF files are the outputs of this UGF to script in data.df, which is the step of this matrix and computation. And we're not going to cover this, but just remember these three of them are the output of the last step. And then these three of them will determine your the representation in the dynamic axis. So this MI is the number of imaginary time point in the IR grid, and this TNLB is the iron file for the fermionic and bosonic function. So essentially, in UGF2, all the dynamic quantity, we use a set of pre-compute IR non-uniform grid and the corresponding Fourier transformation matrix stored and pre-computed temporarily in this folder, but like this could be moved to somewhere else, and just like if it does, we just check the screen website. So it will contain all of the documentation. So essentially, what this file has is it has lambda, which is the control parameter in the IR representation. And you can check in this two reference, and in principle, your lambda should larger than your beta times your energy window of the system. So this is a systematic, this is system dependent grid, but in practice, these are the only file. So essentially, the lower temperature or the larger energy window, you need a larger lambda. And in most of the practical use, the largest lambda I'm using is 10 to the 6, maybe 10 to the 7 you could use, but that's the practical usage. So this, and then this Ni represent the number of imaginary time point. So if you parse TNL and TNLB as this 10 to the 6 underscore 168, that means you're going to represent your time tau domain using 168 points used with this lambda equals to 10 to the 6. So lower temperature or larger energy window, we need a larger imaginary grid. So more detail can be found in the two previous talks in the group. And essentially, both of them, each file contains both the fermionic and bosonic information. So so far at this moment, both of them were you just parse exactly the same file to post the option. Yeah. Maybe at the end we'll just remove one of them. So okay, go back here. So this is the basic parameters. So those are like how define your systems. And then the first one is the most important one. which determine the SCF type of your solver. So which is the MB, like the different choice of the MBPT solver, and you just port as partially forward shift to or GW. And this one result, this is just a result file to store the active file to store the result. And if you set this as true, then the program will just read the result, which is this file, the already existing file, and then restore the same calculation. So if you want to run Hartree-Fock, you simply just fill in all these basic parameters and then specify SCF underscore type equals to Hartree-Fock, HF. And if you want to run the two component relativistic Hartree-Fock, you just set SCF type equals to HF X2C1E and then X2C plus 2. That's it. Then the computation bottleneck in Hartree-Fock step is the exchange diagram, which scale as nk square n to the fourth, which n is the number of orbitals. So during implementation, we have the NPM parallelization over the INK independent cable, which is this axis. So for each k independent k, each NPM process will process it parallelly, and then so the maximum number of MPA job should be INK, maybe difference of spin vector. So the self-consistent GW, if you want to run the non-relativistic or spin-free, just simply set SCF underscore type equals to GW. If you want to run the two component one, this is GW underscore X2C1E and X2C plus 2. So here is we have a bit more sophisticated ampere parallelization scheme, which is controlled by this n-tau spin prox, and this parameter determine the number of process for the secondary of the ampere parallelization on the tau and spin axis. So if you just look at this equation, which is one of the bottleneck in the GW self energy, this is the evaluation of the spin direction, and this building block is what we so-called auxiliary polarization function. And this is like GG, and you have this fitting integral on the both ends. So this one, this Q, for each Q, the equations are independent to each other. And for different tau, the equations are independent to each other as well. So we have a INK dependent Q point, and we have NI dependent tau point. So if once by specifying this, we're going to split, we're going to have this number of top ampere process along this axis, and then the rest of them is we're just assigned to this, or we're going to split this into different groups. So suppose we have an ampere process and n-tau spin prox equals to x. So then the number of process on the z tau axis will be x, of course, and then there will be n divided by x groups on the q axis. So you essentially divide the total number of process into by this number to several groups, and each group will deal with one Q point, and then for each group, all the divers will process the tuple for a given Q point. If you want to do the CUDA GW, then this is exactly the same. You simply add the CU prefix which in front of your SCF type. The parallelization scheme is a bit different. Now we have this ampere parallelization over Q axis, which is similar to the CPU one. And for this case summation, we have this asynchronous strings for the summation. But this will automatically determined by themselves, so you don't have to worry about it. The only thing is third layer of parallelization is along this tau axis. Now it's defined by these anti-batch parameters, which we use this as like the batch to do the batch version of, as a reference to do the batch version of the ZGen. So you have, if you, by default number is 1, typically with these first two layers, like you already use most of the computing power. But if the system is really small, then you can change this from away from the default value, which is 1, and then to see maybe you can get an additional speed up. We also have this iterative solver parameters, which is already carefully covered by Pavel. And essentially what this means is this is the central object in our program. So you have this iterative solver. It means you need this self-consistent loop between these two equations. So if you simply update the G using this new sigma, and then you update the sigma using the new G, and keep updating naively, for a simple system, you could achieve the convergence. But in many cases, it could be slow or maybe even doesn't converge. So in that case, you need some more sophisticated iterative solver. So this is the simplest one. You mix the output of this iteration with the previous iteration, and you also try the DIS, and the more sophisticated one can be found in Pavel's talks. So now it's already in the last step. This is a silicon as an example. I'm using the GTH-DZVP basis with pseudo potential GTH-PDE. So assuming I have run this UGF2 screen init data df.py, then this screen will generate this input IH5, this df underscore int, df underscore object_int with 3 files. The input IH5 contains all the one-body matrix elements, and the df int contains the cooling density cooling integral for GWGF2 with the Meson constant correction for the finite size effect. And this df underscore h object form int contains the density integrals for the object form. So this is the batch script I typically use, and so you specify this from the PyCF output, and you specify TNL and TNL underscore B with using the same file, and this is your output file, and this is the number of process in your NTOS the second layer. So in that case, you will have 64 process to do the parallelization over the K axis, the Q axis. So these are the basic parameter files, and if you're not quite sure what or this value should be, most of them above this line are just what define your system, and this could define this input H5. So if you just look at the input H5, it contains all the PyCF output. If you want to analyze your PyCF output, you could just also look at this file. Essentially, all this file define your system, and it's contained in this or stored in this. And then you also have this Fock matrix, which of course will be read by UGF2 as well. And the non-interacting Hamiltonian, the overlap matrix that depends on determine your orbitals, the basis, like functionality, your basis. Like I say, the UGF2 code assume this Gaussian block orbitals. So what it means is like but in practice, what we does is we just read all these matrix elements as an input. So if you have other program and then you are able to generate this input H5 as using this exact the same format, the UGF2 code is able to compute it as well. So this fog and non-interacting Hamiltonian overlap has this dimension. So one thing could be tricky is like we have a very crude symmetry with this inversion one. So this nk is number of your k point, and number of reduced k point is called ink in the presence of inversion symmetry. And this is determined using our script. So you could just check with this one. So this is the output file. We'll store all the output by iteration, from iteration to iteration. And this energy slash second is the correlation energy, and then energy slash hardship is algebra energy. And you also have this Fock matrix, the correlated Fock matrix, and the Green's function and the self energy. And one thing to keep in mind, now all the output metrics are stored in this INK, not NK anymore. So the dimension could be different between the output and the input. And we also have like the tau mesh of the Green's function. And one subtle thing is the tau mesh we're actually using is the IR tau mesh plus the two endpoint where tau equals to 0 and beta. So if I'm using 168, then in practice there will be 170 tau point. Okay, so that's the last one. Some comments. For the besides this one, of course, the GW scale as in tau and NK squared and else to force. So larger tau point will definitely give you like slower computation, and then this the most importantly this NAO, which depend on your system skill, yeah, not very well. And typically typically 10 to 20 iteration you need to reach the self-consistency. For very problematic system, you definitely need more. And the practical beta, which is the inverse temperature, we typically never use anything smaller than larger than 1,000. So larger than 1,000, which means with 1,000 corresponds to the room temperature. So if you're interested in like system like superconducting system or like anything with like couple 10 Kelvin, this is not at this moment. And of course, for the system definition, the Gaussian basis is somewhat complicated. You need to be careful about this basis of convergence, and in many times you don't actually have a good enough basis at all. Even you couldn't even consider convergence. Sometimes you just don't have the basis set. So this is bad, but on the other hand, sort of expected. This itself is I think this itself is a community in quantum chemistry, so it's not a simple problem you could easily solve. And of course, you have to check your calculation with respect to the size of K-mesh, because it will suffer from the finite size effect. And typically, 6x6x6 is good enough range. So for metal, you probably need a bit more. And the larger the unit cell, the less K point you will need, because the larger unit cell, you have a smaller first brilliant zone. So in principle, the number of K point sampling will be small, will be less. This step, especially electric standard computation, especially density fitting the part, could be very time consuming. And sometimes even for some systems, sometimes even slower than this step, which somewhat unexpected, but I guess this is what it is. And there are several attempts to like speed up this, which could be checking, especially the second paper. And some of them are also like PySafe is also trying to improve this. So I can imagine this will get better, but like at this moment, this one could be very time consuming, and the density output integral could be very large. For like very challenging system, it could take like a couple of terabytes just for one system. Yeah. Yes. So I have several ways to speed this up. So if you actually having this, and at the end definitely would like put this in the UGF2 code. But if you're having trouble with this step, you can contact me, and then maybe we can work this out. Yeah, that's it.
All right. Thank you.